Today, we're going to peel back the layers on a technology that is absolutely essential to our modern lives, but it's almost completely invisible. I'm talking about thin films, these microscopic coatings that power pretty much everything, from the phone in your hand to the satellites orbiting the Earth. So let's dive in.
So, to get us started, here's a little riddle for you. What in the world do a high-tech solar panel and, a regular old bag of potato chips have in common? The answer is actually pretty fascinating, and it gets right to the heart of what we're talking about today.
And the answer is, they are both products of an invisible revolution. They're engineered with these incredibly thin, super precise layers of material. You know that crinkly metallic layer inside the chip bag? Yep, that's a thin film of aluminum, and its whole job is to keep your chips fresh. And the solar panel? Well, that's made of multiple thin films, all designed to work together to turn sunlight into electricity.
So what exactly is a thin film? Okay, technically, it's a layer of material that can be anywhere from a few atoms thick, we're talking fractions of a nanometer, all the way up to several micrometers. But here's the crucial part. These aren't just random coatings. No way. They are meticulously engineered to create very, very specific properties, whether that's optical, electrical, or mechanical. Now, you might be wondering, how can something so incredibly thin be so powerful? Well, it all comes down to its atomic architecture. The way the individual atoms are arranged inside that film basically dictates everything about how it's going to behave. And there are really two main ways these atoms can be arranged. On one side, you've got a crystalline structure. Just think of a perfect, repeating stack of bricks. It's super orderly, rigid, and dense. Then on the other side, you've got an amorphous structure. This is more like taking those same bricks and just tossing them in a random pile. It's disordered, not as dense, and usually a lot more flexible. Now, neither one is better, they're just different tools for different jobs. And this chart just shows you the difference perfectly. Crystalline quartz and amorphous glass are made of the exact same stuff, silicon and oxygen. But just look at that density difference. The super-ordered, crystalline structure of quartz lets it pack in more material, making it about 20% denser than the jumbled-up amorphous glass. That right there is the power of atomic arrangement. Okay, so how in the world do you build something so precise on such a tiny, tiny scale? I mean, you definitely can't just paint it on. Forging these films on the nanoscale requires an incredibly controlled environment. The single most important thing you need to make a high-quality thin film is a vacuum. We're talking about a chamber where we've pumped out basically all of the air. And why? Because at the atomic scale, even one single stray air molecule is like a giant boulder, a massive contaminant that can completely ruin the film's properties. And just look at how dramatic the effect of a vacuum is. At normal, everyday atmospheric pressure, a single contaminating layer of gas molecules will form on a surface in just 3.5 times nanoseconds. That's ridiculously fast. But in an ultra-high vacuum, that exact same process takes around 7 hours. That gives us the perfectly clean slate we need to build our film, literally atom by atom. Okay, so we're in a vacuum. How do we actually build the film? Well, the first major method is called physical vapor deposition, or PVD, and the name really tells you everything. We're going to physically move material from a source onto our target surface, which we call a substrate. A really common type of PVD is called sputtering. You can basically think of it as an atomic sandblaster. First, we fill our vacuum chamber with a harmless gas, like argon. Then we energize it and use an electric field to slam these argon ions into our source material. This impact literally knocks atoms off the target, which then fly across the chamber and stick to our substrate, building up that perfect thin film one atom at a time. Now, the second main method is a totally different ballgame. It's called chemical vapor deposition, or CVD. And here, instead of physically blasting atoms around, we're going to use chemistry to actually grow the film. The best way to think about CVD is like microscopic baking. We put our substrate in a chamber and we heat it up. Then, we introduce some very specific gases. We call them precursors. When these gases hit that hot surface, they trigger a chemical reaction. And one of the byproducts of that reaction is the solid film we want to make. The film literally grows right there on the surface, almost like a perfect crystal forming. It's pretty cool.
So this is where it all comes together. By choosing our atomic architecture, crystalline or amorphous, and by picking our creation method, PVD or CVD, we get this incredible level of control. We can literally design materials with properties that are perfectly tuned for a specific job.
And this is the real aha moment. We're not just making things thinner, we're building materials from the atom up to give them brand new abilities that just don't exist in the natural world.
And the things we can do are just amazing. In optics, we can create mirrors that are so reflective they're used on the James Webb Space Telescope. Or we can do the complete opposite and make anti-reflection coatings for your glasses. We use a film of a precise thickness to literally cancel out reflections using light wave interference. Wild, right?
When it comes to electronics, thin films are, well, they're everything. The tiny little wires inside a computer chip, those are thin films. The insulators that keep them from shorting out, also thin films. And the magic behind your phone's touchscreen, that's a thin film of something called indium tin oxide, a material that's brilliantly engineered to be both conductive and transparent. Think about that. Something that just doesn't exist in the big, clunky macro world.
And we can even engineer them to be incredibly tough. That gold-colored coating you see on high-end drill bits, that's a film of titanium nitride, and it's unbelievably hard and wear-resistant, making those tools last so much longer. We can design films to fight corrosion or even make them biocompatible so that a medical implant is safely accepted by the human body. The possibilities are just endless. So with this technology, we're building materials from the atoms up, giving them properties that you just can't find lying around in nature. It's a total shift in how we think about making things. You could say the future of material science is, quite literally, thin.
So where's all this headed? Well, we're now getting into something called band gap engineering. The easiest way to think about it is like precisely tuning the electrical personality of a material. By stacking different ultra-thin films together like they're atomic-scale Lego bricks, scientists can create totally new artificial materials with custom-designed properties. And this isn't sci-fi, this is the real technology that's building our next-generation lasers, super-efficient solar cells, and even quantum computers.
We've basically figured out how to build things one atom at a time. And as our tools get even more precise and our understanding gets deeper, the real question becomes, what totally new physical properties, what new technologies, what new possibilities are just waiting for us to discover at this incredible invisible scale?